All right, so what we want to do here at the end, our last two lessons here in this unit are dealing with looking at it as a rate of change, using derivative as a rate of change, not just in motion problems. And then our last lesson is using critical values and those max and min values to actually optimize situations, finding the best solution in a given situation. Okay? Now, as we look at rate of change, all right, we often get kind of stuck into this rut of thinking of this only in terms of motion. Okay? But the fact of the matter is, no matter what our function represents, the derivative gives a rate of change. Okay? It gives a rate of change. So if we have a cost function, if we're a manufacturer, then the derivative will give us our marginal cost. What that means is, like, if it costs you a certain amount to produce each item, when you produce X number of items, when you produce more, each item might cost a little less because you're kind of, you buy your materials in bulk, you buy, your workers are already there, the lights are already on, you're already paying them for the day. So if they're able to get 100 made instead of 80 made, then it's going to cost less per unit to make them.
And that's a
Okay.
per unit is marginal.
The cost per unit, and really it's the rate of change in the cost overall. So it is the price per unit given that you produce a certain number of units. Okay? So like I might be able to produce, if I produce 100 units today, they might cost me, $20 a piece to make, but maybe my workers are working slower or whatever happens, I'm only able to produce 80 units that day, then the cost per unit just went up, because it's not like I'm paying my workers less or the materials cost less, So you have that kind of a trade-off, and this is how a company might optimize their profits. They would use a marginal cost function in helping them figure out how to optimize their profits. Area. We could look at how something is growing, and not just area but also volume, and we can figure out how fast it's growing. Okay? For example, we could have how fast a tree is growing. If we can come up with an expression or a function to model its size after a given number of years, we can tell how fast its radius is growing or something like that, or how fast its area is growing or the volume by taking the derivative. Also, if we have a model for a population, and that could be like population of a city, or it could be like a population of a bacteria or something like that, we can look at the derivative and find a growth rate for that.
Would it
This
always
is
be a
how.
growth rate, or could it be like a negative growth rate, or would be like a death rate?
Well, you could still think of it as a growth rate, but it would be negative. Just
Right.
like velocity is negative when it's going down, positive when it's going up. If our population was decreasing, our derivative would be negative. Okay? So you still have those concepts of increasing and decreasing. And we could even use the second derivative to see, is our population growth speeding up, or slowing down, or is the trend pushing it even more in a positive direction, or are we still growing but that growing is tapering off? That's a positive velocity but a negative acceleration. So you can tell a lot of those things using the same types of stuff that we've been doing, just in different contexts.
So would this be like allowed to make you, or allowed for a company, or if someone was trying to find out statistics of the population, make predictions about where the growth would be in a couple years' time?
Yeah, any kind of modeling or something like that. If you've modeled your population rate and you're reaching like capacity for your city, but according to your model, you see that your growth is actually slowing, you might have a little more time to prepare than you thought. Okay? Or you may realize, you know what, it's slowing so much,
It's not much.
we're really not going to need to expand like we thought because it's slowing so much. Eventually, it'll probably level off or maybe even start declining. Or if you see that start to slow, okay, what can we do before this becomes a negative trend? What can we do to kind of kick that back into gear and get it moving faster in the right direction? Okay, those are all different things that you can use different models for. So it's kind of neat stuff. Here's one kind of an example what I was talking about with that marginal cost. Here a company has figured out the cost of producing X items in a factory. Okay? So the raw materials, each material, if this is in dollars, let's say, the materials to make it are $5 for the materials. So for every 1 unit we make, it's going to cost us $5 to make it. But we also have these fixed costs, what's the electricity, all this other kind of stuff that we have to pay. And then we also have labor. Labor will be dependent on how many units we produce because, we might have to do overtime, or we might have to, if we have people going full time, it might increase because now we have to give them benefits and that sort of thing. So you have all of these different things that come into a cost function like this. But look at what we can figure out. If we find the derivative of this, the derivative is easy at this point. Okay, we have c prime of x. We'd have 0.00039 x squared plus 0.004x plus 5. Okay. The marginal cost when 50 items are produced, 150 items, yeah, is going to be c prime of 150. Okay? So if we punch that into our calculator, we get 14.375. Now, what that means is at this point, each unit is going to cost $14.375 to produce. Okay?
So from that, you could then deduce like what your price would be if you wanted to make a profit.
Exactly. So yeah, if we want to make a 30% profit, then 30% of that added on there, and now we know what we need to sell this thing for. Okay? So that's one thing that we can do. I want to see though, if you look at C, find the difference between C of 151 minus C of 150. Okay, so notice we're plugging this into the original function. Okay? Notice this cost is our total costs for everything, not just per unit. Okay? So if I find C of 151, someone could figure that out. C of 151 and C of 150. Okay, for 150 we get 343375. Has anyone gotten the 151 yet? Okay, so 3,000, what'd you say?
440.
Okay.
21.856.
Alright, since you have that on there, go ahead and subtract the 3433.75, please.
It's the same as the rate of change.
14.4356.
Okay, so notice here, what this gives us here is the average actually between the marginal cost of 150 and the marginal cost of 151. Okay, it's a little bit different. Alright, this gives us the instantaneous marginal cost of exactly 150. Okay?
Oh, right.
Okay, so there's the difference there between the average and the instantaneous. Okay?
So if you were talking about it in terms of acceleration, you talk about the first one as instantaneous versus average?
Well, we wouldn't be talking about acceleration at this point. This would be instantaneous versus average marginal cost.
Right,
Okay?
if it was a different model, let's say.
Well, to discuss the acceleration, we'd have to look at the second derivative and see, is that positive or negative at 150? Okay? So if it's positive at 150, then that means our marginal costs are actually on the rise at that point. So we should actually maybe produce less in order to, minimize our costs. There's gonna be a point where to produce more, it's actually gonna cost more per unit. Because now we're having to pay people overtime, or maybe we're overworking our machines and having to do more repairs, or whatever, okay? But we wanna find that spot, how much do we produce that we can actually sell and minimize our costs? So, that's getting into the optimization that we'll look at in our next lesson, but here, you can see the cost is changing. In other words, our unit price would be $14,375. Okay. All right, here's another one. I like this one because it's got some trig in it. Okay. All right, this will hopefully bring back to memory a trig formula that we had.
Oh,
Okay.
I just said it before.
We had some trig, yeah.
actually, yeah.
Okay.
Right,
We had
Good try.
we're dealing with area. We would use the law of cosines that you were talking about before if we wanted to see how BC was growing.
My bad. That's
But that's okay. You're thinking. That's good. We have a formula here though for area. What's our area formula?
1/2 base times height.
Yeah. Okay. Area is 1/2 base times height. But what if we don't know the height?
Find the height.
If we know, yes. Come on.
Yes.
All right. We have two sides and the angle between them. Do you remember the SAS area formula?
I do.
That was my name. That was my name for it. So,
I do
I
remember.
really wish I remembered.
do you remember what it is?
No, I just remember learning about it.
I remember, yeah, same.
1/2 AB sine of C. Okay. If you remember, just check this out. Remember, here's our height. Okay, if I made this the height, then the AC, that 10, would be my base, right? Okay. So I need to figure out the height. Well, I've got theta, and the sine of theta equals h over 12.
So it'd be 12 sine theta.
So the height would equal 12 sine theta. So that's my height, and when I do 1/2 base, 1/2 times the 10 times the height, there's my area right there. Okay? So our function actually, it says find the rate of change in the area. Well, to get the rate of change in the area, we need to have a function for the area. So our function for the area, A of theta, is, I'll simplify that a little bit, that's going to be 60 sine of theta. Okay? So, with sides of 10 and 12, the area of the triangle I can form is going to change depending on what I make that angle. Alright? So if I have a 30-degree angle, my area is going to be 60 times a half, so 30 square units.
Will that tell us that theta is 60 degrees then?
Well, they tell us 60 degrees. So, here's the thing. What is the area when the angle is 60 degrees?
go over how you like went from 1/2 AB sine C to the area being 1/2 times 10 times 12 sines?
It's 51.96.
These sides are two sides of the triangle,
Right.
and this angle has to be the angle between those two sides. That's why I call this the SAS area formula.
Triangle side.
Are we
Okay.
going to not memorize all of those types of this SAS, the
Formula book, alright?
Yes.
Formula booklet, okay? But obviously the more you know off the top of your head, the faster you'll be able to do it, but that is in the formula booklet. Okay, so if I were trying to just find the area, I would have 60 times the sine of 60.
Which is 52, if you want to round.
Okay, and sine of 60 is root 3 over 2, right? So that's 30 root 3, and you said that's 50 something?
52, I guess if you want to round it. 51.96.
51.96 or 52.0,
Yeah.
okay? Alright, and that's square centimeters. Is that what we're looking for?
No.
You're
Find
for
a rate of change.
No, we're looking for a rate of change. So in other words, this is our area at this moment, but how fast is this growing?
Derivative of
So
that.
can you just do 60 cosine theta?
Well,
Is that it?
we need the derivative, and a prime of theta is going to be 60 cosine of theta. Alright, because the derivative of sine is cosine, right? So what's a prime of 60?
Prime, what, like,
60.
60 cosine 60, which is 30.
60 cosine of 30 of 60. What's cosine of 60?
1/2.
A half, good.
30.
60 times 1/2 is 30.
So it's 30 centimeters per unit of time if we do with seconds, okay, hour, whatever, okay? So that's how fast it's growing at that moment, okay? So we can actually say, actually, it wouldn't be centimeters per second, it would be centimeters per degree.
Right.
Yeah, the unit of measure we're dealing with here is degrees. So it's 30 square centimeters of area for every degree we increase that angle. So if I made it 61 degrees, our area would be approximately 82 square centimeters.
That's a lot easier than to calculate like conversions of if you're trying to increase the area by 2/3 or whatever.
Wait, can you explain that to me again? So it's you find the distance, you find the difference between the two, and then that's what you decrease every time.
Well, according to this, at 60 degrees, we're changing at a rate of 30 square centimeters per degree.
Yes.
Now, as soon as we get off 60, that changes just a little bit. But we can use it to approximate. Like at 61 degrees, since the area at 60 degrees was 52, at 61 it's probably going to be close to 82.
Okay.
Okay? And at 59, it was probably close to 22. Alright? So, you could kind of tell around, 1 degree either way, approximately what it's going to be. Okay? Any questions about that?
Nope.
It's kind of cool.
Actually like that.
Alright?
a lot.
It's kind of cool.
Okay,
So, alright. Now, the rest of this is practice. Here we've got some with profits. T is our time in year. We have different profits based on our time. Here we have the volume of water draining out of a swimming pool. Okay? And they made the volume be 200 times 50 minus T squared cubic meters. Okay. Here we've got another marginal cost problem. Total cost of running a train. Alright, here's the kind of thing where you know, we have to figure out how much it's gonna cost to run a train from Paris to Marseille based on how fast we actually drive it. I mean, how many different variables could play into that?
I feel like a lot of variables.
Okay.
A lot.
If you drive really slow, how many people are gonna buy tickets? Not many. Okay?
If you just drive it really, really
If
fast.
you drive it really fast,
Really, really fast.
there'll be a point at which people stop buying tickets too.
Completely stop.
But also think about like the amount of energy that you're having to pay, you're having to consume, and you have to pay for that as well. So there's all this balance.
I'm okay going to the train.
Okay?
If you're on the train, like if you're running the train, like there's a lot of stuff going on.
Yeah. And here's the thing. This is what the guys, the researchers and things that determine costs of goods, they have to look into things like this. How much are we going to charge for a train ticket? And how fast are we going to drive the train? Okay? Just in that, those are two different functions. Okay? This, and they're all interrelated too. Our velocity is going to impact how many people are willing to buy tickets, but also the cost of the tickets is going to impact how many people will buy tickets. So now we've got to figure out, and when we're trying to calculate profits and things, it gets very, very complex. Okay? So, here's another one where a tank is draining. A temperature, here's the law of cooling.
Whoa.
Oh god.
So it's kind of a cool one. The temperature, you have a liquid is placed in a refrigerator, and it's going to cool down until it gets to the same temperature as the refrigerator. But there's a rate of cooling that takes place there. We can figure out how fast it's cooling off at a given time. Okay? Height of a shrub. Okay. The rate of a chemical reaction. How fast is the rate of a chemical reaction? Okay. Depth of water. Here's the change in the depth of water over time as the tide comes in and goes out. Okay.
In Indonesia.
In Indonesia, yeah. And then here's a rate of change just like the problem we just did. Okay. Voltage. The rate of change in voltage in a particular circuit.
If we were
Okay.
to take the second derivative of all of these functions, what would we be technically finding out the rate of change of the rate of change?
Yes.
So what would that give us?
Well, what might be most useful in those cases is really just even the sign. We can tell at that point whether it's continuing to increase even faster, like if it's already increasing, and then the acceleration is positive, we can say, okay, it's not only increasing, but it's also even getting faster and faster. However, if it's increasing but our acceleration were negative, we could say, okay, it's increasing but it's starting to level off.
Right.
Okay, so that's where the second derivative might come in handy.